Welcome to Electros Classroom series. I'm Daniyal Qureshi. Electrical energy is one of the dominant forms of energy that we use. It is a common belief that electrical energy flows through conducting wires that we have all around us, wires in the form of PCB traces. But this is not true. In reality, electrical energy actually flows around the conducting wires and not in it. Strange, isn't it? Well, it took a long time for humanity to discover this during the practical experiences gained in the operation of telegraph and submarine cables. I was also shocked to know this around 3 years back. And trust me, not even once any of my undergrad profs mentioned this. And it is important to know because when you go into the electrical industry, you need this at different levels, not just in electrical transmission, but also in things like PCB and semiconductor design. And in fact, I have heard from an industry leading PCB designer and electrical engineer, Rick Hartley, that even now, many of the electrical engineers are simply unaware of this phenomena. In this lecture, we are going to have a brief look at this and electrical energy in general, along with a really interesting thought experiment regarding the direction of energy flow. Okay, so first let's see the basic of electrical energy. As you all might know already, that electrical energy is a product of power consumed over a period of time. Now, here, this power is average, and this means the level of power that is maintained throughout 1 hour, or that is the average of all the instantaneous power that a device consumes. So, visually, we can see here is our curve. This axis represents the power consumed, and the horizontal is time. Let's imagine any electrical equipment or device that consumes power. Let's say a refrigerator. So you'll see that the power consumed is not constant, obviously. And let's say that this point is time capital T. So this area which comes under the power curve is nothing but the energy consumed by the refrigerator. Just to give you a sense of how it looks visually. And the thing to note here is that with this changing power, this average is obviously a single value. So what you do is that you take an average of power levels consumed, in that time. These levels are not accurate. I'm just drawing them for representation. So what you do is you can take an average of these values, and that will be your average power. And most of the times manufacturers will give you this average power consumed. Let's say if that is a kilowatt, so this means that your refrigerator will consume 1 kilowatt in 1 hour. Or if we were to rephrase, this means that if you were to just assign a single value to the power consumed will be 1 kilowatt at every instance. So we are assuming that at every point in time between this 1 hour of observation window, this thing will consume 1 kilowatt. But the drawback of this average power method is that you will not get accurate measurements. And so most of the electrical measurement meters actually divide this 1 hour into really small segments. It is better if this measurement window is as small as possible so that it is more accurate, and then you actually record the energy chunks consumed over a period of 1 hour, and you just add all of them together to get the actual energy consumed. And mathematically, we can represent that total energy ET P1 into T1 plus P2 to T2. And in most of the measurement cases, these time intervals are actually fixed. That's the observation window. So we can take it common. So P1 plus P2 multiplied by the observation window time T. And for the units, we can see from here, power is in watt And time in metric it is seconds, but we usually for billing purposes we actually take 1 hour, so it will be watt hour. And since this quantity, even this is like very small, so we usually bill it in kilowatt hour, and that in some countries is denoted by a unit. Okay, so let's see how exactly electrical energy is delivered. As I mentioned in the beginning of this video, what we have been told is that electricity is delivered when we see flow of electrons, and that's what delivers the energy. But this is not true. So according to them, the conventional direction of current flow is from the positive terminal of the source or battery to the negative terminal. However, the electron current is in opposite direction. So these are the electrons moving through the conductor. So according to this logic, electrons actually travel the entire circuit. But this is not what happens, because the actual velocity of electrons, known as drift velocity, is very, very less. And it is barely enough for the electrons to even move, let's say, millimeter. This is actually an exaggeration, but they barely move from their original location. And from here, we can see that we have electrons flowing out of the battery in one location and moving into the battery in other location or other terminal. So how exactly is energy delivered if the energy is indeed in electrons? That is the question. So let's see then what is the mechanism of energy transfer from the source to the load. When we connect the energy source in the circuit, in this case the battery, we see that the electrical charges almost instantaneously builds up and extends over the conductor as surface charge. So on the positive side of the battery, you will see the positive charge getting built up, whereas on the negative side, you'll see negative surface charge all along the length of the conductor. And the remarkable thing about this is that this is almost instantaneous, limited by the speed of light in air, obviously, where this experimentation is carried. And you know that whenever there is a charge separation, there will be an electric field. So let's draw some of the electrical field lines just to show you how they will appear, originating from the positive side of the source and terminating on the negative side. Since this surface charge is really spread, you'll see this massive electric field, not just around the battery, but all around the circuit. In the middle of the circuit, it will be something like this, similar to what we see in capacitor. When you have the positive plate and the negative side of the plate, you see this straight electrical field. When it goes outside, it will be opposite. And as I said, this will extend all the way to the load. So this is how electric field looks outside of the wires, but there will be another internal electric field inside the wire that will make the electrons, the free electrons that are available inside the conductors, to move and drift in the direction that's known as electron current, opposite to the direction of conventional current, which is known as simply as electric current. Also, we know very well whenever there is a current flowing through conductor, there is an associated magnetic field generated around the conductor, which is governed by the right hand rule. So we can also determine the direction of magnetic field generated outside the conductor. And here it will point upwards from this side. And on the other side, it will be just the opposite, because the current is flowing in reverse. Now, to answer the question of exactly how the energy is transferred to the bulb, even though the electrons are not even completing a single circuit or they are not continuously flowing, barely traveling a very small distance, we can refer to a very smart guy, John Henry Poynting, who came up with the Poynting vector. Now, according to him, the Poynting vector actually points to the direction of energy flow. So let's start our analysis. Actually, first, let me make one more magnetic loop around the battery, and the Poynting vector will denote by yellow. So according to him, if we follow his rule, then the Poynting vector actually points out of the power source, actually perpendicular to it. And interestingly enough, if we keep doing this all across the circuit, you will see that this Poynting vector follows the wire or the conductors towards the load, that is our light bulb. And same is the case with the other side of the circuit as well. Even though the electrons are moving in exactly opposite direction, but still the Poynting vector is still pointing towards the load. So this is the beauty of Poynting vector. You see, this is a simple DC circuit, but what if we apply this to an AC circuit? Still, you'll see, even though in AC circuits we have current simply flipping, electrons simply flipping the direction, switching the direction, just oscillating back and forth about the mean position, we will still see the Poynting vector originating from the energy source and going towards the load. So for the positive half cycle of the AC power, you'll see current flow in one direction on the upper conductor, while in the negative half cycle, you'll see the current direction flipped, which is also the case in the lower conductor. Even after that, you'll see the Poynting vector correctly pointing towards the load. My favorite science YouTuber, Derek Muller, has made a fantastic video on this topic in depth. So definitely go and check out that. And I would like to also briefly discuss his main experiment, which was like this. So consider we have a bulb and the two terminals, and we have a power source here and a switch. And these conductors are really long. I don't remember how long, but really long. So this distance is really long. The length is really long as compared to this width. I think it was 1 meter or even less than that. So his question was that when you turn on the switch, what will happen? And how fast you will see that bulb light up. So with our normal understanding, one would say that the energy will have to follow the complete path and then reach the bulb. But this is not the case. If we see it from the perspective of electromagnetic waves, as we just saw, that they just radiate outwards. So according to this Poynting vector, so we'll see that even though this wire is really long, you'll see a portion of the energy, not the entire energy, but a portion of the energy will instantaneously be reflected on the load side. So we should see this light up, or this bulb light up almost instantaneously, if we consider that even a portion of energy will or can light it up. Now, if this seems complicated to you, there is another perspective to think about this. So, if you are more comfortable in electrical explanation, so here we go. You see that these long conductors, they are spaced apart, and as we already discussed, that electric field will instantaneously be present after we flip the switch. So once we press the switch, we complete the circuit, and we can also represent this as capacitance on both sides, because these are just conductors separated by space, even though they are short circuited at the ends. But still, if you see what is present immediately in the vicinity, so you'll see that these are nothing but capacitances. So just by using capacitive coupling, you can imagine, because when you press the switch, it is actually a transient signal which can easily pass through this capacitive coupling. And this is similar to what happens when you connect a capacitor in an AC source. You still see the current, even though this capacitor seems open circuit, right? But effectively, there will be current across this capacitance, and this light bulb will light up. So we can conclude from this that electric energy indeed is transferred through electromagnetic fields. So here in this experiment, you can see that we are essentially bridging this gap. And so energy is not taking up time to travel all this distance. Some chunk of it is being delivered instantaneously, and the rest of it will obviously be through this long path. Please don't mind the direction. Here, what I'm trying to say is that the energy is actually delivered by electromagnetic waves. And from the same experiment, we also see that there is no difference between an open circuit or a closed circuit, because here, instantaneously, there is no way for the information to be conveyed instantaneously, because you have to follow the rules of physics. Nothing can travel more speedily than the speed of light. So at the moment you turn on this switch, the circuit doesn't know if it is even open circuited or closed circuited at the ends. Even if this is open circuit or closed circuit, in the transient state you will see no difference, and still the light will light up. But only in the case of open circuit, the light will remain on for just the transient. And when the circuit or the current or the signal that travels then knows that there is an open circuit, only then will there be no energy transferred at the load side because of the reflections at the open circuit end. Now, I would like to extend this discussion to PCBs. In PCBs, we know that there are different layers that we use to form traces. Here, you can see if the top trace is having positive charges and the bottom trace is negative, so you'll see an internal electric field between the two traces, which is similar to what happens in capacitor. And obviously there will be a magnetic field associated with it that I won't draw, but you get the idea. And this medium in between them is typically FR4, that changes according to what you want. But as we just saw, that because the energy is delivered through the electromagnetic waves, so which is traveling in this material FR4, so all the physical characteristics of this material will affect how energy is delivered. So things like electric permittivity, magnetic permeability, even physical things like spacing and geometry. Geometry, as you guys might know with electrostatics, if you have a sharp object or sharp surface, there will be more charge accumulated on that as compared to rounded object. And just to describe, the electric permittivity is nothing but the ability of a material to sustain electric fields. And same is the case with magnetic permeability, how well that material can handle magnetic fields. If it is a poor medium that cannot handle magnetic fields, it will actually impede it. And similarly with the electric permittivity. So now the question is that why do we care at all? The reason is that you guys might know about characteristic impedance, right? So because we have different kinds of signals flowing through the traces on a PCB, mostly they are digital signals, but really high frequency signals, high frequency digital, and analog signals. There you need to be careful about characteristic impedance. This thing is really important. And when you see disturbances in any of these physical things that we just saw, electric permittivity, magnetic permeability, spacing, and geometry, if any of this changes, we'll actually see this characteristic impedance changing. And if this thing is not uniform across the trace, then we'll see reflections, and they are not good because we lose energy. We cannot transfer the maximum energy that could have been otherwise. Plus, on top of that, there is also leakage, leaked energy that goes out of the top or bottom depending upon where it is located. But this is also true with transmission lines, submarine cables. Whatever is right after it can also leak energy into the surroundings. With transmission lines, we see that we hang them high enough so that they um, don't interact much with the ground. If they do, then you'll see significant amount of energy being lost as leakage into the earth. And if you would like to know more about this in depth, you are free to check Alpha Phoenix video. He had made a really good video about the effect of the surrounding medium, surrounding the conductor. What happens when you submerge it in water versus simply suspending it in air. With his practical experience, you will actually see that there is a delay in the signal received just because of the surrounding medium. It's that crazy. Okay, so now after all of this explanation, some of you might have this question that if the energy actually flows in the electromagnetic field, then why do we even need conductors? And this is a very fair and obvious question. I also had the same question, but its answer is not that complex. We can use the analogy of waveguides, if you know. So we have these different shaped hollow structures that are used to guide electromagnetic energy, and many of the times it's some kind of electromagnetic wave, like can be microwave. And this waveguide essentially confines the EM, electromagnetic wave, inside this so that we can make it travel long distances. And this logic, this exact logic, can be applied to electrical energy as well. So you can see wire as waveguides that actually guide the electrical energy. So even though the actual mechanism of energy delivery is through the electromagnetic waves, but we do actually need current for our devices to function or our equipments to function, but that is a byproduct. And to take this discussion further, you shouldn't be surprised to know that electrical energy doesn't need any physical connection to flow, right? There are many examples of this. Something as simple as transformer. You know that we have primary, we have secondary on the other side, and energy simply flows through magnetic coupling. So there is no physical connection. We can also see another example of simple antenna, a dipole antenna, which radiates energy. And these days, we even have devices that can purely operate on the energy that is received or extracted through this radio wave. The only problem with long distance wireless power transmission is that you lose a lot of energy quickly. And also we have medical risks associated when we transmit really high power. And this is one of the biggest challenges that we face in wireless energy transfer technologies, that you cannot go above a certain threshold that has a potential to damage cells. And so you can see that clearly we don't need any physical wires to transmit electrical energy, but the only advantage that we get by using wires is that it is highly efficient. And just because you are guiding the energy exactly where to go, as opposed to just transmitting everywhere in open space in the wireless energy transfer technology, where results get diminished with increasing distance. All right, we finally come to our thought experiment. This is a really interesting experiment that came in my mind long ago, which is about the direction of energy flow. So let's say that we have a very long transmission line, two wire. Now it is so long and you are somewhere in the middle. Now you don't know which side is source or which side is load. So source or load. And you have to determine which side is which. And you can just tap on this area that is available to you. We have already seen how we can point out the source and load by using physics. But here, this will be an electrical method. So the question is, what will you do? Okay, so there are different scenarios. If we consider case one, if the source is DC, we can simply use what we know, that across the transmission line, there is voltage drop. So let's say that we have one voltage probe here, that is VA, and another voltage probe, that is here VB. So if this is a DC line, we know that voltage closer to the source will always be higher, and that decreases with increasing distance towards the load, because load actually consumes it. So the electrical pressure, voltage as we say, actually decreases, right? And added to the fact that resistance and losses of the line itself decrease the voltage further. So simply by measuring this voltage with respect to obviously the other line, we consider that this line is ground. So if the voltage at the A side is higher, so we know for sure that on this side, source will be closer to the terminal A and load will be on side that is closer to terminal B. Okay, so this was pretty simple, right? But let's go further with case 2. And now our source is AC. What will you do? So if you simply say that you measure voltage at point A and at point B, you should see the same trend and you would be partially true. But the thing is that, if you are measuring the voltage instantaneously, then it is not true, because in the positive cycle you will see that indeed this side, the A side will be higher and the B side will be lower. But in the negative cycle, this will get reversed. So you can't really just tell by measuring the instantaneous voltage. But instead, what you can do is that you can measure the RMS voltage, right? That is very important, and that is also the reason, in AC circuits we always consider RMS values and not instantaneous values, because they don't make any sense, because the current is oscillating, but still, if you take the RMS, that's exactly the actual power of that source or of that AC signal. So the root mean square will always follow the same trend as in DC, and that is also because of the fact that RMS value indeed actually reflects the equivalent DC value that the signal has. So similarly, in this case, if we have VA RMS, if you measure the RMS on both the ends, we will see that if VA remains higher than VB, then again we can say that the AC source is closer to the A terminal and the load is the other. And to visualize it, if we see the instantaneous voltage across the line, what we'll see is that the voltage swings will gradually decrease, which explains that the VA RMS will be higher and the VB RMS will be lower if it is closer to load. Alright guys, I hope you enjoyed the video, and if you did, then please like, share and subscribe. We have really good topics coming up next. In the upcoming lecture, we are going to see principles of generation of electrical energy. We will be moving slowly with time, picking up important fundamental concepts, so that then with a solid base, you'll be able to handle even the most complex problems in electrical engineering. Until then, stay tuned. Thanks for watching and see you there.